you guys have a good weekend?
Yeah.
Oh, well.
Slight emergency, don't worry.
Since you're still smiling, it must be all right. Any questions about anything or things you noticed, or just, open period time here? Anything you want to ask me? Oh, we'll find out the bowling ball today. If you can tell the class is ending and I haven't done it yet, make me do it. I intend to, but yeah, I get carried away sometimes. Lots of fun toys. Okay, all right. That's good. So, we finished momentum essentially, and I left you this as a kind of teaser. We saw what happened, but we'll explain it. Let's start there. I like this demo because of the what it implies. So we have a happy and a sad ball. There's the happy ball and the sad ball. The happy ball will roll down and knock the block over. The sad ball will roll down and it's sad. Doesn't knock it over. It's not a fluke. Boom. But the happy ball will. Did anybody happen to think about it over the weekend? I think maybe some of you did. Any thoughts as to why the happy ball knocks it down and the sad doesn't?
So for the sad ball, exactly the surface is the hard or soft?
These are essentially identical. There's only one little difference. Yeah, you can touch them. And I'll tell you that after I explain it. But the difference between them is essentially they are made of, well, go ahead, slightly different rubber. It's so one will bounce and one won't. But they're the same, essentially the same mass, volume, size, weight. Yeah.
That's interesting.
Yeah.
Well, it's because the one bounces, so that's why it knocks it over, because it gives a bigger force.
Bouncing gives it a bigger force?
Yes. Compression.
Okay.
Because the one that's bouncing is an elastic collision.
The one that is bouncing is an elastic collision. Good. Where the one that stops is an inelastic collision. What kind of energy? Kinetic energy is not conserved in the inelastic, the sad ball collision. Okay, good. You said something.
I was just saying the compression of the ball. I would say compress.
How much they compress. That does vary. They both compress.
But the one will try to go back more to its core.
One is able to rebound. That's the type of rubber, which is why it bounces. Where the other one, that energy does not go back into rebounding, kinetic energy. It goes somewhere else. Good. This is good. See, your eyes are thinking. Want to add anything else? How about way back there? I want more of this one. Why does bouncing mean it applies more force? Why are you saying that? Well, all right. No, that's good, because that's what the book says. Yeah.
Is it because there's more kinetic energy imparted into the object it's hitting?
More kinetic energy imparted into the object it's hitting.
More kinetic energy going into it that has to give equal amount back to make it bounce. So therefore,
Well, let's get into that.
so it's kind of like metal transferring. It feels hotter than, say, like a pillow, but the pillow and the piece of metal are the same temperature. They feel different because they transfer the energy more efficiently.
Yeah, the energy is definitely different. Yes. Which one's which? Okay, the sad ball. It has kinetic energy. We mentioned that. That's the energy associated with motion. And this is how you find it. 1/2 times its mass times its velocity squared. So if something's moving, it has kinetic energy. These both have kinetic energy. They're the same mass, and they come in at the same velocity, don't they? So these actually come in with the same kinetic energy. But this one stops. Its kinetic energy goes away. It's not conserved. It's an inelastic collision. That energy was transformed and went somewhere else. It didn't return to this, and it must not be transferred to the block sufficiently. This one does rebound. Boom. It has some kinetic energy afterwards. But notice it starts at this height, just like our basketball and tennis ball. It doesn't come back up quite as high. So it's not moving as fast up as it was down. So even that one wasn't a perfectly elastic collision. Some of the kinetic energy got transferred into something else, but not as much as the sad ball. On that vein, let's go back and look at momentum. The ball comes in. It has momentum, mv. Do you agree that both of these balls, when they get right there, they have the same momentum? They're the same mass. They've started from the same height. They fell for the same time. They have the same momentum. When they hit the block and they're in contact with the block, what's their momentum? It's not a trick question. Are they moving when they hit the... No, so their momentum's 0. So we're going to stop at the block first, and there the momentum is 0. So it's a collision. And you can see that there was a change in momentum. And what was it? It's how much in momentum there was to begin with, minus how there was at the end. So each one, when they're in contact with the block, has a change of momentum of mv, the same amount. Remember, change of momentum is impulse, which is force times time. So they're in contact for a certain amount of time, and there's a force applied on the ball and on the block, equal and opposite. That's what the balls feel. It's enough to stop the balls, and it's enough to stop the ball. That's as far as we've gotten. But something else happens for the bouncy ball. The sad ball stops there. Nope. That one, it stops. But this one turns around and bounces back the other direction. So ideally, it bounces, oh, for crying out loud. Comes in, bounces up. We're going to idealize at this point. Comes in at a certain momentum. Let's say it comes out with the same momentum to make things easy at the moment. It's a little less. Now I should actually put the minus sign there because it's a vector. So the bouncy ball, what's its total change in momentum? It comes in with some momentum before it hits, stops, turns around, and comes back with the difference between the initial and the final. Because I get confused, let's write it out more. Change in momentum is the final momentum minus the initial momentum. The final is minus mv minus the initial, which was plus mv, which makes a total of not 0, negative 2 mv. Pause, let you write that, sink in. Another way to think of it, we saw it had a change of mv when it stops, but now it's going to go from 0 back to mv, another change of mv. So the magnitude of it's twice. Well, there's the real way I'd like you to think of it. The bouncy ball has twice the change of momentum as the sad ball, the non-bouncy ball. Change of momentum's impulse. Impulse is force times time. If the bouncy ball has twice the change of momentum and twice the impulse, it feels approximately twice the force to pull that off. Think of it this way. It takes force to stop it, but then it takes force to kick it back. So the happy ball feels twice the force on it. It also exerts twice the force on the block. So, again, happy ball bounces off, and it's that kick that adds the extra force. Where this one gives no extra kick. The energy is absorbed into the molecular structure of the rubber. That's where the energy goes. So, question. Next time your enemy pushes you out of a 10-story window, because, you know, it could happen, or you fall out of an airplane and your parachute doesn't go, how would you like to land? You want to bounce? You want to go flat? Why do you want to bounce?
Because it's going to make my landing easier.
Well, it's the force, right? How much force you're going to feel. Which one of these exerts more force on the block?
The happy one.
Yeah, the bouncy one. It exerts enough force on the block to knock it over. But by Newton's third law, that means it's also feeling more force. So when you land like this, it'll hurt more than if you land like this. So even though I started out saying this is the happy ball, this is really the happy ball. Real life application. Drunk drivers. When they're in an accident, who usually gets injured less? Yeah, the drunk person. It's typically because they're relaxed. They have slower reactions. And so they don't tense up and they get all tight and they don't rebound. They don't bounce off as much because they're not as rigid and solid. They usually kind of... So if you go limp and you relax, harder said than done in the moment of collision there, but if you could relax and go splat, you might survive. You still break every bone in your body, but maybe you survive. Whereas if you bounce, you will feel more force.
I have a question.
Yes.
And if I am, my parachute is doesn't open, or I am pushed from a 10th floor building, whatever. But if I go and where I am going to land is water, if I go with the other, well, I'm going to sink. And I cannot emerge from the water.
Well,
The happy ball is going to allow me to bounce out.
you're going to sink regardless after you hit. And it's actually a myth too. From high up, water's just as hard as ground. Which is why, again, back at Park City with the ski jumpers, they bubble up air into the water to cushion it so that it softens their landing. But yeah, you landed in the ocean out of an airplane versus the ground. Yeah, it don't matter. You're dead. Well, usually. Yeah.
So what is like the material difference?
I have them written down. It's just two types of rubber. They have a different molecular structure, and the idea is one of them, the energy is stored in the ball molecularly. It gets compressed, but it rebounds and gives it back because the molecule can flex like that. The other one, the molecule, the energy goes into it and it changes it enough that it doesn't kick back. It stays in here. So technically the sad ball, nope, the happy ball, the non-bouncy ball, it will get a little warmer because that kinetic energy has to go somewhere. Sound, heat, and it's probably mostly heat in this case. So that one gets a little warmer with each bounce than this one. But it's the molecular bond. I can show you pictures if you're interested later, but I don't remember the fancy names either, like norberine or something like that. So another idea, karate chopping, or next time you're in a fist fight, right? In theory, I can hit you in the face, and you want to follow through. You got to hit them solid, right? If you want it to be effective. But if you could bounce off their face, it should impart more force than just staying with their face. If this is your face, if you just hit it, go with them, as opposed to hitting them solid. You still got to hit them long enough and bouncing off.
But as a bounce,
As long as they don't give. If they give, then you can't win. So that's another thing. If you're getting hit, give. It extends the time of the collision. So the force you and their fist feel is less. So give with the punch. If you try to be rigid, it'll hurt more. Anyway, there you go. Life lesson here in physics class, survival tips. So here's some other collisions. You probably have all seen a Newton's Cradle. That's what these are called. This is a bigger, fancier one. If you take this sphere, it comes in and collides and momentum as well as energy is transferred. And probably most of you know what's going to happen. And I can't leave this set up in my area back there without, every time somebody goes by, they have to mess with it. It's fun. So this one comes in with mv momentum. This one comes out with mv momentum. Momentum's conserved. They're the same mass. It's like the air tracks, carts. So whatever momentum this comes in at, this one comes out at. And because they're the same mass, that also means they have the same speed. Now, why doesn't 2 come out? 1 could come in, has mv, right? Well, if 2 came out, what would their speed be? There's twice the mass now. To keep the momentum the same, we'd have to have half the speed. You double the mass, the speed needs to go down to keep the ratio mv. That theoretically could happen, but you can see it doesn't. Why? What if I start with 2? Maybe 1 could come out twice as fast, but 2 come out at the same speed. Why? Well, roughly, energy is conserved too. In this case, it's mostly an elastic collision. They're bouncing. And so if you had 1 come in, what's its kinetic energy? That. So that means the kinetic energy ideally has to be that after the collision. If 1 came out, you can see it'd be the same. If 2 came out, let's do it. 1/2. We have twice the mass now, right? But how fast are they going? Half the speed. Why? Because momentum is conserved. If you double the mass, the velocity goes down.
What do you mean by conserved?
Energy cannot be created nor destroyed. It's always conserved. You can't just like make it disappear or have it come out of nowhere. So if this one starts with so much energy, you can't just have that disappear. It can be transformed into something else, like heat, and it's no longer kinetic energy. But in an elastic collision where they bounce, ideally the kinetic energy is conserved. So we'll look at the kinetic energy, and the kinetic energy this guy starts with should be what we end up with. Again, the momentum, if it starts with mv and you come out with twice the mass, then you got to have half the velocity to keep it mv again. So if we just plug those into kinetic energy, what's this come out to be? 2m v squared over 2, and that one squared is 4. So that is 2mv squared over 8, which is 1/4 mv squared. Kinetic energy was not conserved. That's why it doesn't come out with 2 balls at half the speed. Or at least both these conditions have to be met in this, and it doesn't in that case. So it doesn't happen. My point here is that, again, momentum, total momentum is always conserved. You use that in your problems to figure things out. And kinetic energy is always conserved in elastic collisions. They have these toys. Here's a small one. I used to love these as a kid. Anybody remember these? Clicker clackers or something, and you can bounce. You can go around. Whoops. See how it stops at the bottom until the next one hits it? That's like the air tracks. They're the same mass. So it comes in, transfers its momentum, it goes out. Goes out. And then let's see, I haven't done this in a while. But anyway, good example of collisions and momentum transfer there. Here's another toy. Remember how we did the basketball and the tennis ball? Well, this one has 4 balls. So if we drop it, they'll come down, and as these come back up, they collide with the other ones. The smaller ones transfer some of their momentum into the bigger ones. They don't bounce as high. But the bigger ones also transfer their momentum into the smaller ones. And because they're smaller, less mass, less inertia resistance, they'll accelerate greater. And watch this red ball if you can. Hit the ceiling. So you can get an impressive amount of energy, kinetic energy, into that ball because these guys transferred it into it through a collision. Okay, clicker time. I got 2 questions I want to ask you. Oh, one turned off, the other did not. EGA1. Doesn't like me today. Let's just try the resetting thing first. There we go. All right, now you can log in. I'll go ahead and open the question, so once you get there. What? I'm giving you time. I just started. While I'm stalling, because it's the first one, you log in. I'll turn the lights back on so you can see this better, but there's 3 new unassigned clickers. So somebody has started responding in the last week or so, but didn't register their clicker correctly. Thus, if these are your device ID numbers, please email me and tell me as such. I can hook you up and make sure you're getting credit for your responses, because these 3 people are not getting credit. So basically you got a big fish coming up on a small fish not moving. He comes in, eats it, and keeps on moving. So how does the big fish's speed compare after he eats versus before? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 3/4 of you think it's less than before. You're correct. What's the total momentum before the collision? Big fish, small fish. Big fish, small fish. Does a small fish have momentum?
No.
Does the big fish? Yes. So let's call it mv. The total is mv then. So afterwards the total has to be mv, right? Okay, after he eats it, what's the new mass? It's the two together. We just increased the mass. Mass went up. So what happens to the combined velocity? It has to go down to keep total momentum conserved. Or think of it as the little... Nah, that didn't work in that case. That works. Questions? Okay, same collision, big fish, small fish. Spare you from reading. What happens to the big fish's momentum? After the collision, let me remind you, the 2 fishes are together. The big fish is fatter now. He just ate the little fish. He weighs more. What happens to his momentum? His speed went down. We just did that. What happens to his momentum? Well, polling's open. Answer away then. And if you were paying attention, I already gave you the answer. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ta-da. 76 say it's the same as before. You're right. So I won't lie, I'm a little concerned about those that missed this one. Can you ask your questions? I might be embarrassed now, I'm sorry. But the momentum before has to be the momentum after. The big fish had all the momentum before. Now he just ate a small fish and got fatter. They're together. It's part of the big fish. It has to be the same momentum as he had before. He weighs more, so his mass is more. So he's going slower. But the momentum is the same.
Is that because the small fish was...
It's part of the big fish now.
So is that because the small fish was at rest?
Yes, small fish was at rest, right, because initially he didn't contribute any momentum to the system, yeah. If the small fish was moving initially, things would be different. Total momentum would still be conserved, but yeah. Okay, those are the two I wanted to ask you for that. So now that the lights are on, double check your device ID if you're here today. If it's one of those, please email me as such so I can connect you. So we talked about, I mentioned a story about oomph. And this is in chapter 7, the story. I just forgot when I was telling you. It was Émilie du Châtelet in the 1700s. Who, like Galileo, just did an experiment that I described last time and figured this out because they were confused. This oomph, they didn't know what it was, but they wanted to know, was it proportional to mass times velocity? Or was it proportional to mass times velocity squared? I guess proportional to... So in other words, was it proportional to momentum or was it proportional to energy? In this case, we now know kinetic energy. And they did tests. And they found out that if it came in with this oomph, something was transferred to something else, or it went so far, or it made it deformed something a certain distance, it crunched it, and it was proportional to velocity squared. So they knew this was energy. I'll give you an example. I bought some Hot Wheel cars. It's always fun when you can use Hot Wheel cars. So I bought a bunch of the same. So this is not a foolproof demonstration, but it's fun. Because the Hot Wheel cars are cheap and they don't always act the same. But the idea is that I'm going to rotate this piece of wood like this. And so you can see this one covers a smaller distance, so he won't be traveling as fast. This one's twice as far away. He'll be going twice as fast as that one. 3 times, 4 times. The one out here has to go faster. So this one will have more momentum. It'll also have more kinetic energy, which is what I'm emphasizing here. I'm going to then put on the brakes. It's just like if you brake in your car. If you're going yay fast and you hit the brakes, in this case I'm going to hit a brick wall. Okay, a lead brick. They'll stop, but they'll keep moving, right? Inertia. They're in motion. They got a certain speed. They want to keep going. Let's see how it works. That worked. I'll try it again. This one went further because it started with more energy. And the distance it went is a lot further than this one. Now, like I said, this isn't perfect. But if you look from my angle or from above, this is not a straight line. If it was straight, that means this oomph would be proportional to momentum because this was going so fast it went yay far to stop. Took that much energy. Well, this one was going twice as fast. It had twice the momentum. It went a little more than twice the distance to stop. This one went a little more than 3, and this one more than 4. It's not linear. It actually curves slightly. Let's try it again and see what happens. Might be pushing my luck. Well, that one went off at cattywampus. It's a technical term. Get the point. Again, curved more. My point here is that yes, it's proportional to velocity squared. And the energy it takes to stop it, what force is stopping these cars, by the way? Friction. It's exerting a force, and air resistance. There's a force pushing backwards on it. It's applying energy. It's transferring energy to the car. Because they start with kinetic energy, over here. But that goes away. It's transformed into something else. Heat, a little bit of sound, from the heat from the friction. And how much energy does it take to stop them? Well, it's proportional to how much energy it started with, and that's the velocity squared. There's another form of energy called potential energy. That was like the energy that got stored in the happy ball. Dang. It compresses, just like a basketball. When you hit it, it compresses, and momentarily it stores energy. I think of potential energy as energy that's stored. It has the potential to do something. It's also the energy associated with position. There's different types of potential energy. We're going to deal with gravitational potential energy, how it's located in the field of gravity. But there's also electric potential energy, elastic potential energy, that's like in the basketball, or a spring, or a rubber band. I can put energy in this rubber band. It now has the potential to do something. There's potential energy in it. You know what happens if I let go, right? That energy gets converted into kinetic energy because it's going to move. Yeah, you got it. Shoot it back if you like. Springs do that. Okay, it's happy. I'm going to stretch it. There's now energy stored in the spring. It has the potential to want to come back. You know, if I displace it, should have got a smaller mass. We'll just have little ones. There we go. But it's position, how it's stored. Specifically with gravitation, it's like this. Where's my chalk? Where does a block want to be? Down here at height 0. That's where it's happy. So in order to lift that up, will that take energy? Do you have to exert work on it? Yeah, you lift it up to say here. Put it on the shelf. Some height, I don't know, 2 meters, let's say. Well, to get it up there, I think your gut tells you have to exert energy. So you do work on the object, and now we say it has more gravitational potential energy than it had down here. Relative to the floor, it has no gravitational potential energy here. Relative to the floor, it has more. And how much more? This is how you figure it out, mgh. Look at this. What's mg? You remember? Yeah. What's that represent? It's a weight. It's a force. That's Newton's second law. That's the weight of the object. You'd have to exert a minimum force of that, right, to counter its weight. And then you move it a certain distance up, and it now has that much energy. So it has mgh up here. To get it there, to transform between types of energy, or to move something, I've already used the term, but it's work. Think of work as a way to transfer energy. I used to, as a kid, well, actually, even when I was sitting right where you guys are, think and call work a form of energy. I don't like that anymore. Don't think of work as a form of energy, because an object, you can't say an object has work. This book has work. That doesn't sound right, even to physicists. It doesn't have work, but it has the ability to do work on something. You know, I could put a nail down there or an egg, right? And if I push it off, it's gravitational potential energy it has relative to the floor. It's like it's storing energy. I let it go, whoosh, it'll fall. It gets converted to motion, kinetic energy. That kinetic energy will hit the egg, and it'll do work on the egg and smush it. So it doesn't have work, can't possess work, but it can do work. It's a way to transform or transfer energy. You can go back and forth. That's what this is for. This has gravitational potential energy relative to here. If we say this is H equals 0, then it has no gravitational potential energy there. I do work, my chemical energy, to get it up here. How much energy did I give it? Do you realize you could find out? You weigh it, you get its weight, mg, and you measure this distance, right? mg times that distance. You now know exactly how much energy this stores. And you know exactly how much work I did on it, right? I have to exert a force on this. How much work did I put into this? Well, figure out how much potential energy it now has, and because energy is conserved, that's how much work I had to give it to get it up there. And if I let go of it, I could ask you, how fast will it be moving down here? Because it'll have kinetic energy there. It's moving, right? What does all this gravitational potential energy convert into? Kinetic. Do they have to be the same amount? They better be. This can't have any more kinetic energy than energy it started with here. So again, you can play the game. Total energy is always conserved. Total energy. Here it has gravitational potential energy, right? But no kinetic. Here it has kinetic, but no gravitational potential. So the total, they just kind of swap. What about right here? What kinds of energy does it have? Right there. Both. How does the gravitational potential energy here compare to here? Correct, it's less because it's lower down. How about its kinetic energy here compared to here? Greater, because it's moving faster. See how as it moves down to here, the gravitational potential energy decreases because it gets lower, but the kinetic energy increases because it's going faster. But the total stays the same. They can just slosh back and forth, just like this. Potential, kinetic, potential, kinetic, potential, both. Only potential, only kinetic, both. You get the idea? Now, do you notice something? Whoa, wait, I thought I just said total energy is always conserved. Somehow it's slowing down and not returning as high as it can. So we're losing some potential and kinetic energy. Where is it going? Friction causes heat. Heat's another form of energy. So if we count the heat, the total energy is always conserved. Could you tell me how much energy goes to heat? Absolutely. Let's say it starts here and gets to here, right? It's like the bouncy ball. Dang it. Here to there. That difference, right? You would know how much energy it starts with, right? Gravitational potential. But it returns to here. It only has so much gravitational potential. Wait a minute, we lost this much? Find the difference? And that's how much went to sound and heat. I loved conservation of energy because before it'd be like, I don't know how to find heat. We haven't even studied thermodynamics. It doesn't matter. Through conservation of energy, you could figure it out. Before, too, we would time how long something fell, right? And we could figure out how high up it was based on how long it fell. Or vice versa. If we knew how high up we started, we could tell you how long it takes to hit. We could figure out how fast it was going with our motion equations. You can do that now with conservation of energy. If it starts with gravitational potential, does it have any gravitational potential energy right before it hits the table? Right as it starts to hit. Does it have any height? No. So it has no gravitational potential energy. So where did all that go? Into kinetic. It's now moving right before it hits. You could know exactly how fast the thing's moving. You following me? If you start here, mgh plus 1/2 mv squared. It comes down, and right before it hits, it's still mgh plus 1/2 mv squared. If you start not moving, and you end up moving, the total energy before is all this. This is 0 to start with. And down here, you have no height. It all got converted into kinetic. So that must equal that. Does that make sense? The total before equals the total after. In this case, we just had a 0 and a 0. You can solve this. The masses cancel. It doesn't even matter the mass. I could do this with a car. And if I dropped the car from the same height as I dropped this, they would both be going the same speed right before they hit. Because it doesn't care about mass. Air resistance aside. If you solve this, if you care, let's see, that'd be the square root of 2gh. So all you need to know is how fast it's being accelerated down and how high you started with. You need to know how fast something was going. Volunteer. Who's going to trust all this physics stuff? Because I'm going to attempt to scare you slightly. Who's brave? All right. Oh, you got a question, Eddie. Go ahead.
Is that velocity, is that for, like, free fall?
Yes. The example I was doing was free fall. Drop.
Without, greater heights, you'd have to discount or be in a vacuum where you don't.
Yeah, if air resistance doesn't slow you down, you'd end up going that fast falling from that height. Or rolling from that height, if you could eliminate friction. So like this case, where it rolled down, I started this high. It has that much gravitational potential energy. So if I roll down to here, how fast is it going right there? Total energy is still conserved. It was all potential here. There's no potential down here. So where did it go? It's all kinetic. So that applies again. That would tell you how fast it's going down here. Do you realize that dropping something from this height, it'd be going a certain speed right before it hits the ground? That's the same speed it would be going after it rolls down the same height? Because it started with the same amount of energy. Arm's getting tired. If it starts here, it has so much energy. It can fall straight and take a shorter distance, or it can roll down the incline and take a longer distance. But it'll still end up with the same speed, the same kinetic energy, right before it hits the ground. All right, any volunteers yet? Oh, thanks. Stand right here, pretty please. And you're the only one that really has to stay alert. Yeah, it's going to swing at you. So here's another a pendulum. Oh, back up. Let's say this is height 0. So no potential energy. To raise it up, I have to exert what on it? Work. A force. I'm going to apply a force. I'm putting energy into the system. All right, I guess a little closer. We're going to have you hold that where my hands are at, on this side. And hold it right up here to your eyeballs. Now it has potential energy. Any kinetic? No, she's going to let go of it. It'll turn into kinetic down here going fast. No potential. Then it'll lose kinetic as it slows down, but gain potential. and then back. And we'll see what happens. Right? Touching your face.
I've made a huge mistake.
All right, whenever you're ready.
Okay, I'm trying to lean forward.
Do-do-do-do-do-do. Do-do-do-do-do.
Ah, I knew I would. You can't not.
Want to try it again?
Okay,
See, now you know.
I'm ready. I'm
Yeah,
ready.
I even know, but I still flinch. Oh, you moved forward a little.
Shit.
Thanks, I appreciate that. Well, the idea here is what? If it starts with so much total energy, can it magically gain more energy as it swings? No, never. So it can never come higher up than you started with, unless someone adds energy to the system by pushing it or something. And because of air resistance and the friction up there, it slows down a little. Some of that energy is converted into heat. Thus, it's no longer potential back at this point. I like doing it too. Anybody else want? Let's see. Whew. I haven't done it in a while, so I'm just feeling the mood. Zoop. All right. So, work. I actually give you that formula. Is found a couple ways. Work is the way to change and transfer energy. So when you're talking about something in motion, that causes a change in kinetic energy. If you push something, you exert a force on something, you're applying work, and you cause it to speed up or slow down, start moving or not. You can also think of work then, it's a force. Impulse was a force times time. You applied a force for a certain amount of time. Work is applying force, but it doesn't care how long you do it. It cares how far you did it. So this is often referred to as the work-energy theorem. Just 'cause work causes a change in energy, and usually we're talking about motion. I like this one even better. Work is force times distance. It's that force exerted for a certain distance. It's very similar to impulse. That was force for a certain amount of time. It was like force times how long? Well, how long in time? You got impulse. How long in position? You got work. But my last question for you is, I'm going to do work to run up the stairs. I have no gravitational potential energy. I'm going to exert work, change my kinetic energy, and start moving. And now I have gravitational potential energy, no kinetic. So work was converted into kinetic energy, and kinetic energy was converted into potential energy. I have it now. How much work did I exert? Well, if I could figure out the force I had to apply and the distance I moved, I could figure out how much energy I put into the system. But you guys know this. If I do it at this rate, did I exert more work or less work? Your gut wants to say more, right? How much potential energy do I now have? The same. So that tells me, wait a minute, I must have exerted the same amount of work to get up here. And ideally, that's true. Work doesn't care about time, how long it takes. So it was the same amount of work, whether I ran or not. We'll discuss this next time, but power is what we're dealing with there. Power is the rate we use energy. Rate of using energy. And that is how fast or slow we use energy. So it's like work over time. That's where the time comes in. It's the rate that you use energy. So if I get up there quicker, there's less time. The denominator's smaller, right? It was faster. Do you see how that means I exerted more power? I definitely exerted more power, but I used the same amount of work to get to the same height. Think about that, and we'll start there next time.